Hello everyone, my name is Pyarasani Bharat from ITA section. Today I am going to talk about hydrogeochemical modeling for total hardness in aquifer of urban areas. Understanding the chemical composition and properties of groundwater in urban aquifer. Hydrogeochemistry deals with the chemical characteristics in groundwater systems. It studies interactions between water, soil, and geological formations. Understanding hydrogeochemistry helps evaluate water quality and usability. In urban areas, this field is vital for managing pollution and hardness issues. An aquifer is a geological formation that stores and transmits groundwater. They can be conformed or unconformed based on surrounding rock layers. Aquifers act as natural reservoirs, supplying water for domestic and industrial use. These chemical compositions depends on geological and environmental factors. Hardness is primarily due to dissolved calcium and magnesium salts. It affects water quality, causing scaling and reduced soap efficiency. Temporary hardness arises from bicarbonates, while permanent hardness comes from sulfate or chlorides. Understanding hardness is essential for water treatment and quality assessment. Urban aquifers accumulate hardness due to natural mineral dissolution. Anthropogenic activities like swelling, dis- discharge, and industrial influence add to it. Construction materials and runoff increase ionic concentration in groundwater. Understanding sources aids in developing mitigation strategies. Modeling helps stimulate chemical reactions within groundwater systems. It integrates physical, chemical, and environmental data for analysis. Such models predict changes in water chemistry under various conditions. They support decision making in sustainable groundwater management. Total hardness represents the combined concentration of Ca plus 2 and Mg plus 2 ions. Assessment determines the sustainability of water for domestic and industrial use. High hardness indicates high hardness levels indicates mineral rich or contaminated aquifers. Monitoring hardness is crucial for public health and infrastructure protection. Parameters include pH, temperature, ion concentration, and mineral content. High CO2 levels promote dissolution of carbonate rocks, increasing hardness. Electrical conductivity reflects and ionic strength of groundwater. Electrical conductivity reflects the ionic strength of groundwater. Regular chemical analysis ensures reliable modeling and prediction. Chem- Calcium and magnesium are the primary contributors to water hardness. They originate from dissolution of limestone, dolomite, and gypsum. The ratio provides insights into aquifer rock composition and reactivity. Qualifying these ions is essential for hyd- hydrogeochemical assessments. Carbonate hardness is caused by bicarbonate salts removable by boiling. Non-carbonate hardness results from sulfates or chlorides requiring chemical treatments. Distinguishing between two helps in selecting appropriate softening methods. Modeling identifies their relative contributes to total hardness. Proper sampling ensures reactive representative water quality results. Samples are collected in clean containers and analyzed using standard methods. Parameters like pH, TDS, and ion concentrations are measured. Accurate data is vital for effective hydrogeochemical modeling. Models can be empirical, geochemical, equilibrium based, or reactive transport. They, they simulate dissolution, precipitation, and ion exchange reactions. Softwares like Pre, PreQ or WaterQ is commonly used for analysis. Model outputs guide water quality management decisions. Ion exchange occurs between groundwater and aquifer minerals. This alters the ionic consumption and hardness over time. Ca- Cations exchange processes replace Ca plus 2 and Na plus or other ions. These reactions are key compositions in hydrogeochemical models. Urbanization increases impervious surface and reduce infiltration. Wastewater discharge introduce pollutants into aquifers. Altered hydrology affects ground, groundwater recharge and quality. Urban aquifers often show higher hardness due to anthropogenic influence. Water pH affects the stability of calcium and magnesium compounds. Low pH increases dissolution while high pH promotes precipitation. Balanced pH is crucial for maintaining stable water chemistry. Monitoring pH helps interpret hardness variations across aquifers. Data interpretation. Data interpretation involves graphical and statistical analysis. Hypo- Hypos and stiff diagrams helps visualize water type and chemistry. Correlations between reveals dominant geochemical processes. Interpreted data supports sustainable water management strategies. Softening processes remove hardness causing ions from water. Methods include lime soda treatment, ion exchange, and reverse osmosis. Preventive approaches involve pollution control and aquifer protection. Modeling aids in designing suitable treatment strategies for urban areas. Hard water causes scaling in pipes and reduce appliance efficiency. It can affect crop yielding when used for irrigation. High hardness pose minor health concerns but affects taste. Managing hardness ensures environmental and economical sustainability. Studies in urban regions reveal spatial variation in water hardness. Hydrogeochemical modeling predict future quality trends under stress conditions. Comparative analysis shows the effect of urbanization on aquifer chemistry. Case studies demonstrate the practical application of modeling approaches. Summary. Hydrogeochemical modeling is essential for understanding groundwater quality. Total hardness serves as a major indicator of aquifer health. Urbanization and pollution influence hardness through chemical processes. Scientific modeling supports effective water resource management. References: Sphere and MC Card Chemistry for Environmental Engineering. River Geochemistry of Natural Waters. APHA Standard Methods for the Examination of Water and Wastewater. IARE Engineering Chemistry Course Notes. Department of IT. Thank you.